Thank you. And this is based on joint work with Justin Holmgren, who's at Princeton University. So first, I want to start by talking about multiplayer games, which I'm sure many of you are familiar with, but let's go through what a multiplayer game G is. So a multiplayer game will consist of k spatially isolated players, P1 through PK, and a referee. And what happens is this referee samples k queries from some distribution and sends the ith query q sub I to the ith player p sub I, and receives back an answer from each player. And then based on the answers in the queries, he decides whether the players have all won or lost the game. And we define the value of a game to be the maximum winning probability of any player strategy. Now, multiplayer games are interesting because they provide a model for studying how spatially isolated players can coordinate their answers. Because here, each player is only receiving his query, but depending on what physical theory we consider, the players can actually coordinate their answers. So A sub I can depend on Q sub J. Now, some physical theories we may consider include first the classical physical theory. So in the classical world, if we have spatially isolated players, then the players cannot communicate at all. So each answer must actually only be a function of its query. And we say that the classical value of a game is the maximum winning probability of all classical strategies. Now, if we allow the players to share an entangled state in a quantum world, then the set of answers actually can depend on the entire set of queries, as long as this dependency can result from sharing an entangled state. And similarly, we can define the quantum value of a game as the maximum winning probability over all quantum strategies. Now, lastly, and the topic of this talk will actually be on non-signaling strategies. So here, we simply require that the players' answer distributions do not imply communication. I'll say more about what this formally means. But for non-signaling strategies, we have the non-signaling value. So let's talk about non-signaling strategies more formally. So a strategy is actually just a set of answer distributions, one for every set of queries. And when the referee sends a vector of queries, Q1 through Qk, the players sample some set of answers from the corresponding distribution and sends those answers back. Now, we say that strategy A is non-signaling if for every pair of queries, Q and Q prime, and subset of players such that the subset of players S is receiving the same queries in both Q and Q prime, then the S marginals of their answers are the same. So essentially, the players in S are sending back the same answers distributionally. So in other words, what this means is that for a non-signaling strategy A, we can actually define S marginal distributions for every S, where the input is going to be a subset of queries and the output will be a subset of answers. And to be non-signaling simply means that we can define these marginal distributions such that they're consistent with the actual strategy A. So let's walk through a more concrete example of what it means to be non-signaling, to be using a non-signaling strategy. So again, at the top is just the definition again. And so basically, we can consider two different queries here, Q and Q prime. And for example, let's say that the first and second players are receiving the same queries in both of these instances of the game. Then to be non-signaling, we just need that the 1-2 marginal distributions are the same. So we need that when we sample answers from the strategy on Q1 through QK, or when we sample the answers from the strategy on Q1 prime through QK prime, that the distributions of A1 and A2 are the same for both. So you might ask, why would we want to study non-signaling strategies? Well, first of all, they generalize quantum strategies. So they assume any k spatially isolated players have to be using a non-signaling strategy in any world where Einstein's theory of special relativity is just assumed to hold. However, the constraints on answer distributions is also simple to write down and to study. We just saw the mathematical definition of non-signaling strategies. It's easy to write down this definition on just the answer distributions, whereas to capture quantum strategies, it can be a lot more complicated to capture what it means for players to just share an entangled state. And lastly, there are some applications in cryptography, namely if you're familiar with fully homomorphic encryption, non-signaling strategies capture the computations that can be performed on ciphertexts which are encrypted under different secret keys. So now I want to jump to talking about parallel repetition, which is a pretty natural operation that you may want to perform on a game. Basically, we say that the n-fold parallel repetition of a game G, denoted G to the n, consists of n different independent instances of the original game. So the referee here in G to the n will sample n independent sets of queries from the original game. And to each player, he will send the n queries that correspond to that player and receive back n answers from each player, and then decide whether the players have won or lost the game. And the players win this repeated game if and only if every instance of the original game is won. So if and only if the referee of the original game would accept the ith set of answers for the ith set of queries for every I. Now, we want to think about what kind of strategies players can use in the parallel repetition of a game. And in particular, we know that the players could simply apply the most optimal strategy for the original game to every instance of the original game independently. So this shows us that the value of the parallel repeated game is at least the value of the original game to the nth power, right? And now this raises the natural question of whether the value of the n-fold repetition actually has to equal this value. You may think that, well, in the n-fold repetition, the best that the players can do is to simply apply the most optimal strategy for the original game independently to every instance. But this is not actually true. There's counterexamples even for n equals 2. So the question that we are left with is, can we at least upper bound the value of the n-fold repetition? And intuitively, we would like to say that the value of the n-fold repetition at least decays exponentially with n. And this is what's known as a parallel repetition bound. And again, one of the original motivations for parallel repetition is for hardness amplification of a game. For instance, if we have a game whose value is a constant and we repeat it n times, then we have that the value of the repeated game is at most inverse exponential. So parallel repetition bounds have been widely studied for the 3 different strategy classes I mentioned. So for 2-player games, we actually have a pretty decent understanding of the n-fold parallel repeated game. We have exponential decay bounds for classical and non-signaling strategies, and we have an inverse polynomial bound for quantum strategies. Now, for multiplayer games, for 3 players or more, we really don't have a great idea of how the n-fold parallel repeated games can behave. So the best that we have in the classical case is a 1 over inverse Ackermann bound. So we know that the value of the game does decay towards 0, but quite slowly according to this bound. Potentially quite slowly according to this bound. And then for quantum and non-signaling strategies, we don't actually have any bounds for general multiplayer games. We do have exponential decay bounds for special classes of games, and I won't get into those here, but they include things such as connected games in the classical case, fortified games, anchored games in the quantum case, and complete support games in the non-signaling case. And the first contribution of this work actually is we show that you can't actually have a parallel repetition bound for general multiplayer games against non-signaling strategies. So more concretely, we show that there are games such that the n-fold repetition will have a non-signaling strategy that has constant value for any n. So no matter how many times you repeat the game, there will be a non-signaling strategy that wins with some constant probability. And this is quite surprising because at least in the quantum and classical cases, which have been quite well studied for some time, researchers do believe that there should be some kind of parallel repetition bound. So more formally, our results are the following. So our first result is that for every k at least 3, there is a k player game such that the non-signaling value of the n-fold repetition is at least a constant for every n. Our second theorem is what we call a dichotomy theorem. We show that for any game, the non-signaling value will be at least a constant, or it must decay inverse exponentially. So this is quite interesting because in particular it rules out the possibility of there existing games whose n-fold repetitions have values decaying, say, inverse polynomially. So there's only two possibilities for the behavior of the non-signaling value of the n-fold repetition. I'll kind of briefly outline the main steps for the second theorem. So Lansing and Winter introduced this generalization called sub-non-signaling strategies. So these strategies generalize non-signaling strategies. And they actually show a parallel repetition theorem for sub-non-signaling strategies. So they show that if the sub-non-signaling value of a game is less than 1, then the value of the n-fold repetition decays inverse exponentially. We show that if a game has a sub-non-signaling strategy that always wins, then we can actually construct a non-signaling strategy for the n-fold repetition that has constant value for any n. And so this shows that we have either inverse exponential decay or the value of the game stays above a constant. The rest of this talk is actually just going to focus on the first result. I want to give kind of a very concrete proof of the first result. Namely, I'm going to show a 3-player game and construct a non-signaling strategy for this 3-player game that always wins with some constant probability, no matter how many times you repeat the game. So the game that we're going to consider today is going to be called the Disagreement Game. So how it goes is the referee is going to sample a set of queries from 011, 101, and 110. And each player is going to respond with a bit. And the referee will accept if the two players that receive one send back different bits. So the referee will accept if these players disagree. So first, let's see why this game can't always be won by a non-signaling strategy. So let's let A denote the player's non-signaling strategy. And we can see that with probability 1/3, the referee is going to send 011 and just look at the 2-3 marginal of the answer, right? And similarly, with probability 1/3, the referee will check the 1-3 marginal of A on 101, and with probability 1/3, he'll check the 1-2 marginal of A on 110. But we know that since A is a non-signaling strategy, these three marginal distributions have to be the same as these three corresponding marginal distributions on A of 111. This simply follows from the non-signaling constraint. So actually, we can think of this disagreement game as the following. This game is equivalent to the provers sending a triplet of answers sampled from the single distribution A111. And then the referee randomly chooses a constraint to check. He randomly decides to check whether two of the answers disagree. And the punchline here is, well, any triplet of bits can only pass two of these checks, right? If we have a 3-bit string, it can only satisfy two of these constraints. So the probability that the referee accepts in this equivalent view of the game is at most 2/3. And so the non-signaling value of our disagreement game is at most 2/3. So you're probably starting to think, well, the interesting thing here is that we had this distribution A111 that, at least for this game, somehow seems to limit the winning probability of non-signaling strategies. And this will be important to keep in mind when we try to construct a non-signaling strategy for the n-fold repetition. So we have now this disagreement game, which is non-trivial to win by a non-signaling strategy, and we want to think about its n-fold repetition. So we're going to construct a non-signaling strategy for the n-fold repetition, and the idea will be to first start small. We're going to start by constructing non-signaling marginals that don't lose this n-fold repetition. So I won't formally say what non-signaling marginals are, but the definition is pretty simple to generalize here. And what we're going to do is we're going to iteratively combine our small marginals to create larger marginals. So we're going to start by defining size 1 marginals, A1, A2, and A3, and these will just be the answer of a single player when he receives just his query. We're going to use the size 1 marginals to construct size 2 marginals. And we're going to use the size 1 and size 2 marginals to construct the size 3 marginal, which will be our full non-signaling strategy. So what does it actually concretely mean to define these marginals? Well, I just want to remind everyone that we're thinking about the n-fold repetition of a game. So the marginal A sub I for I equals 1, 2, or 3 is going to be an output of n bits for any n queries, for any n bits in which form a query for the ith player. And similarly, the marginal A sub ij will be defined for every such query set. And so now let's start with our size 1 marginals. Well, a very simple thing that we can just do is we can just have the size 1 marginals output n independent random bits. And now we want to construct our size 2 marginals. So we're going to first think about the case where we have the nth game, the nth instance of the original game is sending to the ith and jth players the bits 1 and 1. And in this case, we want to just sample answer bits that disagree, right? Because if we sample answer bits that do agree, then immediately this marginal can't be part of a larger answer distribution that would win the parallel repeated game. But this is the only constraint that we're going to place, because otherwise we're just going to sample 2 independent random bits, a sub I to the m and a sub j to the m for every instance of the game. So for every m from 1 to n. So now I want to take a step back and observe that if for every instance of the game, our queries are actually either 0, 1, 1, 1, 0, 1, or 1, 1, 0, then we can define this answer distribution, which will just output a triplet of bits that is only that is random but just subject to the winning. So concretely, what I mean by this is let's just consider the nth instance of the game, and let's say that the j and kth players are outputting 1. Then we just want to output 3 bits for this instance of the game such that the j and kth bits are different. And this distribution A is not a strategy. It's only defined on vectors of queries that are of this form. But the interesting thing is that this A tilde is defined on all queries which are actually asked in the n-fold repetition of the game. And so we can actually consider the notion of its value with respect to this game, and it always wins this game. So we're going to use A tilde and our size 1 and size 2 marginals to construct a non-signaling strategy for the n-fold repetition. And how this will go is we'll have 2 different cases depending on what our query looks like. If every instance of the game consists of a query of the form 0, 1, 1, 1, 0, 1, or 1, 1, 0, we're going to let the answer distribution sample from A tilde with probability 1/3. And with probability 2/3, we're actually just going to sample from our size 1 marginals independently. So what this looks like is with probability 2/3, we're sampling just completely independent random bits across the 3 players for every instance of the game. Now, the second case is otherwise we're going to let our answer distribution simply be uniform across a combination of the size 1 and size 2 marginals. So this is our strategy for the n-fold repetition. And our first claim is that this strategy is non-signaling. So if we have 2 queries, Q and Q prime, which are in the same case, it's not that hard to actually just verify that the answers are non-signaling. The interesting case is when one query, say Q, it falls in case 1, and the second query falls in case 2. Now, if the size of their intersection is 1, so let's just say that the jth player is receiving the same n queries, then just note that any size 1 marginal here actually just consists of n independent random bits. So the non-signaling constraint will hold. Now, if the size of their intersection is 2, so if the j and kth players are receiving the same n queries, then we can check that the JK marginal in the first case is going to be with 1/3 probability sampling from A tilde sub JK, and with 2/3 probability just sampling from the J and K size 1 marginals. And in the second case, we can check that with 1/3 probability, we're going to be sampling from our JK size 2 marginal. And with 2/3 probability, we're going to have a size 1 marginal, which will just have an independent random bit from our size 2, from the other size 2 marginal. And so we get these two marginals for the JK marginals, and our size 2 marginals were actually defined exactly so that A tilde sub JK equals A sub JK. And this is enough to check that A is a non-signaling strategy. Now, we have A, our non-signaling strategy, and we want to show that it wins with some constant probability. And this is actually the easy thing to check here, because the winning probability only depends on the first case, because the first case captures all of the queries that would ever be asked by the referee in the n-fold repetition of the game. And with probability 1/3, we're sampling from this very good distribution, A tilde, which always outputs it accepting answers. So all in all, we have a non-signaling strategy A, which is defined for every n and wins with probability at least 1/3. So I want to give now a recap of this talk. So I started with talking about multiplayer games, which I said are interesting models for studying the correlation between spatially isolated players. And we can consider different kinds of strategies for our isolated players, such as classical, quantum, or non-signaling strategies. And now, for multiplayer games, parallel repetition is a very natural question to ask. And in particular, it's motivated by its potential for hardness amplification. And previous works have shown polynomial or exponential decay for 2-player games, but they had very, very limited results for general multiplayer games. And this work, we focused on the parallel repetition of non-signaling multiplayer games and showed the surprising results that there are counterexamples to parallel repetition bounds. Namely, that there exist multiplayer games whose n-fold repetitions have non-signaling strategies that win with some constant value. And secondly, we show that there's a dichotomy that characterizes the behavior of the n-fold repeated game. That namely, the non-signaling value of the game is at least a constant or must decay exponentially. And a lot of the technical contribution of this work actually goes into proving the second theorem. And I try to give a little taste of how we go from small non-signaling marginals to larger and larger non-signaling marginals in order to construct non-signaling strategies for the n-fold repetition. The full report is on ECCC, and I'm happy to answer any questions you have. Thank you.
Yeah, many thanks for this very interesting talk. So are there questions for Lisa? Yes, there. Okay, I can give you mine.
For each case, did you find one example, or are there many examples?
So there's a counterexample for every k, and we actually, so basically, if the sub non-signaling value of a game is 1, then it is a counterexample. Yeah. And we do have, for every k, some game with a sub non-signaling value 1.
And there are 2 cases, which exponential decay and constant, right?
Yes.
Which do you think is common? Do you have some? I mean, did you analyze this? Which is?
Oh,
common?
more common, or?
Yeah. Which is more common?
We didn't analyze that. I think you'd have to first formalize kind of what like how you're generating games,
Okay.
if that makes sense. Yeah.
Thank you.
All right, I had two questions. The first one is simple. Can you go back to where you showed previous work? You had a place where the quantum bound was tighter than the no signaling bound. And I would have thought that would be impossible, that because the non-signalers have more power than the quantum, how can the quantum bound be weaker in this way?
You mean why this bound is just inverse polynomial?
Yeah, because the non-signaling people should be able to do even more than the quantum people, so their bound should be looser.
I see. Yeah, so the thing is that for that doesn't quite work. Like a bound for non-signaling won't imply a bound for quantum, just as a bound for quantum won't imply a bound for classical. Because when you're looking at strategies, even though when you consider non-signaling strategies, the strategy set is larger. When you look at quantum strategies, it's possible that the quantum strategies that they'll fall into non-signaling strategies, but yeah, the same analysis doesn't apply. I can try to talk a little bit more about it offline.
Yeah, that would be good. It's very interesting.
Yeah, it's a very delicate point because you would think that one would apply the other, but
I do think that.
Yeah.
Except that you're telling me it's not true. My second question is, can you relate this to in non-signaling theories, there's some result like all communication complexity tasks reduced to 1 bit, or something like this. Do you think that's related somehow? Because it makes non-signaling things very powerful. That would feel related to getting a constant winning probability. Like if you turn it to a communication complexity question and then guess the 1 bit or something.
yeah, I'm not familiar with that work, but I do agree that there is like something very subtle about like non-signaling, that if you have some access kind of to the randomness being used in non-signaling strategies, then there is a good amount of power that, or at least some good amount of information that can be in some sense communicated.
Okay, thanks.
Yeah.
Maybe we're going to take one last question. Yes.
Yeah, so you show in this work that there are games whose value doesn't tend to 0, right? But is it the case that the no signaling value tends to something always? Like, I mean, here you have a gap, right? You have like a 2/3 in the non-repeated case and a 1/3 lower bound in the repeated case. Does it behave like, does it kind of tend towards the 1/3, or is there some sharp cutoff, or like, do you know how this behaves?
Yeah. So, are you asking about this particular game?
Yeah, let's say this particular
Sure.
game.
Yeah. So actually, for this particular game, we do have a non-signaling strategy that wins the n-fold repetition with probability 2/3. And we can in our paper we actually do describe this better strategy. It just doesn't fall. How we arrived at it doesn't fall in the framework that generalizes for any game with sub non-signaling value 1.
Okay, thanks.
Okay, so we will have now to free the room for the business meeting, so I propose that we take other questions during the free afternoon or whenever. But let's thank Lisa and Richard also for these 2 great talks.